So this is the second video in a series about the eigenfunctions of the Fourier transform. In the previous video, we talked about the Fourier transform as a review, some properties about it, and then went over some examples. So you can see the other video for what we were going over. Now in this video, I want to talk about some basic sort of linear algebra ideas related to eigenfunctions and such, because that's what the thing is about. It's about eigenfunctions of the Fourier transform. So this series is about. So in order to talk about that, we're going to talk a little bit about eigenfunctions in general, eigenvectors, but we're also going to be talking about some of the symmetries. So what we're going to have is the Fourier transform itself, and then we're also going to have these other operators, and LR will introduce some of these. And these operators will be used to capture some kind of symmetries. And what we're going to have is some kind of, basically, the operators will commute like this. If I do them in different orders, I will get these identities. And so what it'll do is it'll tell me some extra information about the eigenfunctions of F. So let's just do that. So we'll review some of the basic ideas from linear algebra about this, and then we'll continue. So recall from linear algebra that you have A and B. Now, if they are endomorphisms on some vector space, and what that means is that they're just linear operators on a vector space. Basically, you could think of them as matrices. And we're going to assume that AB is equal to BA. So they commute, as people write it as the commutator of AB, which is AB minus BA. Well, if AB is BA, that means this is 0. So we have some operators on a vector space, and we're going to assume that we have an eigenvector. So V is an eigenvector. Sometimes technically people say eigenvector has to be non-zero. So, I didn't technically say it was an eigenvector in these zones. So we're just going to assume this equation, and we're going to see what happens when we apply B to V. So you have A times BV, and this is kind of like a standard property. So, a standard technique. So we have ABV. Now what you do is you use the fact that AB is BA. So you now group A and B, and then you swap them because they commute. So you get BAV, and now you use this identity. So AV is going to be lambda V, and lambda is just a number, so you can pull it out. So lambda BV. So A times this vector BV is lambda times the vector BV. So what that tells us is that A times BV is lambda BV. So, either BV is an eigenvector with eigenvalue lambda, or it's 0. Usually, part of the definition is that an eigenvector is a non-zero vector. And this basic fact here, if you took a course in abstract linear algebra, is related to the idea of if you have two commuting operators, then if you have an invariant subspace for A, B is going to preserve that. So it's related to eigenspace. An eigenspace of A is going to be preserved by applying B to it. So if you have eigenspace, lambda eigenspace for A, so this right here is a vector subspace of V that contains all the eigenvectors of A. Then if you do B applied to that, it's going to belong to E lambda, because E lambda is an invariant subspace for A, and from this commutativity, B is going to preserve that. So it's going to send this into itself. And that comes out in this kind of equation here. Now what we're going to do is review some things related to normal matrices. So you have A is a matrix, or just as any operator. If A is a normal operator, what we mean by that is A star A is AA star. So this right here, you might be familiar with this as Charles matrices, which is that the A star is conjugate transpose. The transpose is where you take the matrix and then you flip the entries, you turn the rows into columns and such. Conjugate just means you take the numbers and you do complex conjugate of all of the numbers in the matrix. Now, a matrix is normal if it satisfies this equation. So A and A star commute. Now, spectral theorem says if you have a normal matrix, so A is a normal matrix, then it turns out that from the spectral theorem is that A is diagonalizable, which is kind of a nice property, but also you can find an eigenbasis, that makes it diagonal. And the eigenbases are going to be made of orthogonal vectors. So it's a very nice property. Being diagonalizable is nice, but also having orthonormal basis is much nicer because it gives you some very nice properties. And what we'll be learning about in the series is certain things that are analogies to things that you learn about in a functional analysis course, which tries to generalize this spectral theorem for not just normal matrices, but also normal operators on infinite dimensional spaces where there are a lot of subtleties and things are way more complicated. But for matrices, you can learn about some of the basic ideas that go into the more abstract functional analysis things. And it kind of gives you like an intuition for what's going on. Because in infinite dimensional spaces, you learn that there are sometimes technicalities and complicated proofs. But for the if you learn what is being generalized for the matrices, so the matrices have nice properties, have certain things when they're normal. If you learn what the infinite dimensional cases are trying to generalize, then you can get a kind of intuition for the things that go right and the things that go wrong and those kinds of things. So it is useful to explore matrices, and that's why we're defining it. We're going over it to give you some kind of idea about what the Fourier transform is going to do. It's actually, Fourier transform is actually going to behave like a matrix in a certain way. It's not going to be a matrix, but it's going to behave like a matrix in some ways. And so you see the Fourier transform is going to be like a nice example of an operator on an infinite dimensional space, as opposed to some other ones which are a little nastier. Okay, so another fact is from the spectral theorem, you can use the spectral theorem to prove this, is that if you have A and B that are normal and that they commute, then not only can you diagonalize each of them with their own orthonormal basis, you can find a joint orthonormal basis. So an orthonormal basis that works for both of them. It's an eigenbasis for both of the matrices at the same time. Now, why exactly is that useful? Well, if you have a matrix B and you have some kind of, you can find out what its eigenvectors are, then it can give you some kind of information about what the eigenvectors of A should be. Because, I mean, you know that there is some kind of joint orthonormal basis. So knowing some information about the eigenvectors of B will help you find things about the eigenvectors of A. And that's kind of the idea that we're going to be doing. So suppose we have F is a Fourier transform. We know that it's unitary, and where it comes from unitary is that it preserves the L2 norm. And from that, it's kind of like a standard thing from functional analysis to show that if you expand the L2 norm, you square both sides and you write it as this inner product here. And if you put this over here using the adjoint, this is equal to this. And then you can show, using polarization identity, that F star F is the identity. That's what this identity gives you. However, because F is, this right here is an isometry property. However, because F is also invertible, it turns out that the opposite identity is true. You have F star is also equal to the identity. And you can check some of these things using some of the stuff we went through. Anyway, so it satisfies these two identities, so it tells you that F star is the inverse of F. So that's just relate. So all these things here, like this, all this work that I wrote here related to this this tells us that f is unitary. That's what it means to be unitary. I was using it earlier, kind of roughly to mean isometry, but it's invertible isometry, so it's unitary. The inversion is basically the Fourier inversion formula is what gives you unitary as opposed to just being isometry. So from the unitary property, which is just this, we know that f star commutes with f. I mean, that's just what this is. F star is identity, and f star f and f star are both the identity, so they commute. So the Fourier transform, I mean, its adjoint of the Fourier transform commutes with the Fourier transform, so f is normal as an operator. In general, unitary operators are normal. And this n operator that we had earlier, which is the f of negative x, if it's the negative sign here, you can show that this right here is a unitary operator on L2 by doing the change of variables that changes x to negative x when you're calculating the norm of a function. However, you can also show it just pretty simply by saying if f is unitary, then f squared is also unitary, because the inverse of n is going to be inverse this, which is going to be its adjoint. I mean, you can commute the squared and the negative. I mean, the inverse. F star squared, that's f squared star, which is n star. So its inverse is its own adjoint. So n is also normal. It's unitary and it's normal. But you could just check it's unitary by doing a change of variables as well. So we have two commuting operators. F is unitary. I didn't say they were commuting yet, but they are commuting. F is unitary, n is unitary, and we're going to have that they commute. So it's going to be kind of like an analog to this. And we're going to use that kind of idea that I mentioned about the eigenvectors to give some kind of extra structure for f for the eigenvectors, and then we'll be able to study them a little carefully. But before we go on to that, I want to mention another symmetry that the Fourier transform has, which is related to rotations. So suppose we have R, which could be some kind of rotation matrix. So this is the orthogonal group on RD. So this is like basically the only part of the talk I'm actually going to be using RD very specially. So if R is an orthogonal matrix, it's either going to be a rotation or reflection or in some combination of those two. What we're going to do is we're going to define using this matrix here, which has the property that it's basically a real unitary matrix. It doesn't change lengths, and it's expressed like this. So this is going to be a real matrix that satisfies this. So it turns out to be the same kind of identities as this. So its transpose is its inverse. It's just a matrix. Now what we're going to do is we're going to define LR of f of x to be f at Rx. So we just put the R on the inside of the x. Now this right here does like a certain kind of rotation. So if we had, this is the domain here, like an R2, so D equals 2. And if R was like a rotation by a certain degree, then f of Rx is basically the same kind of function. But, I mean, suppose the function was 1 here. What would be this function here? Well, you have to rotate it and then find the value here, and that's what the value would be here. So it kind of does this weird thing. People, whenever you do group action stuff, you learn that usually people put the inverses here because it helps make the symmetry kind of nicer. However, I don't really care about the geometric picture, which I was trying to explain in this not very helpful picture. And the point is that I'm going to put the R here, and we're going to see that there's some kind of symmetry here with the Fourier transform. The point is that this is related to some kind of rotation, and that's all you really need to know about it. So with this LR operator, this is a unitary operator on L2. Like I said, it's related to some kind of rotation, and you can check that it is using a change of variables, which is similar to what we're going to do in a second. So I'm not really going to do that. LR is unitary on L2, and not only is it unitary on L2, it also commutes with the Fourier transform. That's why we care about it. That's why I care about it anyway for this talk. So proof. Well, let's do the Fourier transform. We'll rotate it, the function. and then we'll find out what it is at k. So what is that? Well, this part right here says if I do this, apply to this function, that means I just put the r on the inside of the k, and then I calculate what that is. Well, I know what that is. That's just f integral e to the 2 pi I x times the argument rk dx. Now this is the inner product here. The reason why I'm writing it as an inner product as opposed to a dot product, which, you know, the same thing, is because you can do things with the dot product that that are a little bit more natural. I mean, with just the inner product. It's related to this idea, these identities up here, which is that if you have rho x, I mean rx, rk, if you move this over, that's x r adjoint rk, because R is a real matrix. That's the same thing as this transpose. So this is the identity. So this is xk. So you see that if you apply R to x and k on both ends, it's just the same thing as not doing anything and still doing the inner product. Basically, you have two vectors like this, and you want to find out how much they overlap. Well, if you just rotate them both consistently, this is x and k, this is rx and rk. Well, if they still have the same angle and the same kind of relevant position because you just rotated both of them in the same way, then they should have the same inner product. That's the idea. Anyway, so we have this integral here like this. Now, let's calculate what it is. We're going to do a change of variables to make use of this trick here. So what we're going to do is we're going to replace x with rx. Now, because R is an orthogonal matrix, turns out that we're doing an integral over RD. All these integrals have that. I'm just suppressing the notation. It doesn't actually change anything, and so you don't need to write any kind of extra factor. You can just do this change here, and the dx stays the same. So we have the x here, the x here, so we get rx, rx. Now this part right here is the thing that is going to be unchanged, like we said above, all the way up here. So this stays the same, but then the f of rx stays there, f of rx. However, now we get this integral, and this right here is, well, this function is LR of f of x, and that's only inside of this Fourier transform. So it's saying the Fourier transform of this at k. So what we showed is that L, I shouldn't have erased this. It was just for the example. So if you do the Fourier transform first of the function and then LR, it's the same thing as doing the LR first and then the Fourier transform. It doesn't matter what order you do. So that means that they commute. Now, why do we do that? The reason why we do that is so we can get to the standard property, which says if f is a radial function, which means that f only depends on absolute value of f of x. So it doesn't depend, if you have a function on the real line, for instance, it's the same thing. F has the same value here as it does here because they have the same absolute value. If we have a function on R2, then basically on circles, it's constant because a circle has the same distance from the origin, which is just this thing right here. So for instance, an even function on R, or some kind of function like this, or this function, which is kind of like Gaussian. Anyway, it is a Gaussian. That's a kind of higher dimensional space. So if f is radial, f only depends on absolute value of x. We just explored that definition. Then so is its Fourier transform. That is the kind of the takeaway of this property here, as far as symmetries are concerned. So why is that true? Well, the proof is that suppose we have a function g that's radial. What it means to be radial is that it doesn't depend, g of x doesn't depend on anything except for g of x is equal to g of rx for any rotation r, because x and rx have the same length, because r is just some kind of rotation or reflection or something. It doesn't, it's an orthogonal matrix. It doesn't change lengths. Now, because this is true, LRG is going to be G for R, for all R in the orthogonal group. So if we have a radial function f for all R in OD, then we can just calculate something using the Fourier transform, which is the LR Fourier transform. Well, we know that they commute, so you can move this on the inside, LR of f. If f is radial, we know from this identity here that it doesn't do anything. So LR of Fourier transform is the Fourier transform. So we verified that this was true for the Fourier transform, which means that the Fourier transform is radial. So Fourier transform is radial. And that just proves this corollary. So if you have a function that's even, you do this Fourier transform, it should be even. If you have a function kind of has like a nice, it's, you know, constant on circles, if you do its Fourier transform, it will be constant on circles as well, if it's an R2. And that's kind of secretly this example right here. We had a function, a vector that has eigenvalue lambda. If you apply b to it, it also has an eigenvalue lambda because they commute. So here I have a function that's radial, so it has eigenvalue 1 for this LR. If I apply the Fourier transform, then it has eigenvalue 1 for the same operator LR. That's kind of the idea. Now we're going to do it for n. We did it for LR, we're going to do it for n. If f is even, that's the same thing as nf being f. So nf, remember, is the operator that takes negative x. So if f is even, that means it doesn't care about the sign. So nf is going to be f. That's the same thing as being even. Odd is the same thing as, well, the negative sign really does matter, and it makes the whole function negative. So nf is negative f. So what you can do is you took the idea of even and odd, and you express them as eigenvectors, or eigenfunctions, I guess, of n. So this is eigenvalue 1, and this is eigenvalue negative 1. Now, fn is equal to nf. And why is this true? Well, we know that n is f squared. So, I mean, if you just check out what this is, it's just f times f squared is f squared times f, which is true. You can also check this by doing this in kind of change of variables. That's actually an example of this. This LR here, R, if you do R to be negative identity matrix, then LR is just n. Now this right here, it depends on the dimension, but this will be either some kind of rotation or reflection and rotations. Anyway, the point is that LR and n, they're kind of, n is an example of some kind of LR, but also n happens to be Fourier transform squared. So in any case, they commute. So what it means to commute is that if you have a function that's an eigenvector or eigenfunction of n, then you apply a Fourier transform, it will also remain the same eigenfunction. Now, being the same eigenfunction is the same thing as being even or odd in this case for n. So if we have a function that's even, its Fourier transform is even. If we have a function that's odd, its Fourier transform is odd. So here in this this video, we talked about some of the symmetries of the Fourier transform related to commutativity. So we talked about commutativity for matrices and how it's related to eigenvectors, and then we explored some of the things that you could say about it, the Fourier transform, for some kind of symmetry operators that we talked about. So that's going to be the end for this video. Forward to hearing from you, comments, or etc.